Good day, everybody. This is Chris at the Ancient Scholar, and today I'd like to talk about something completely different, and that is I'd like to talk about a little bit about the atom, and specifically I want to talk about the what are known as quantum numbers, and the quantum numbers are a set of four numbers, and you guys should be familiar with these numbers from general chemistry. There's a set of four numbers that basically um, define the electron within an atom, define the state of the electron. And these include N, L, M, and S. Those are the quantum numbers that you're familiar with. And just as a quick recap, these quantum numbers actually fall out of an equation. I actually have the equation right here. They fall out of what's known as the Schrodinger. All right, the Schrodinger equation. And the Schrodinger equation is roughly analogous to the F equals ma. Okay, it's the F equals ma of quantum mechanics. So it is analogous to Newton's second law of motion. It is kind of the fundamental equation of motion, if you will, for quantum mechanics. And I'm not going to spend all day talking about quantum mechanics. Well, in a way I am, but I'm not going to be talking about solving the Schrodinger equation or what goes into it specifically, but just to kind of recap what it is. And we know that when we apply classical mechanics to the atom, we get a model that is just completely incorrect. It just cannot describe the behavior of the atom. And starting in about 1900 to the 1930s, so 30, 40 years is when we really kind of solidified the foundation of quantum mechanics, and starting with Max Planck and the ultraviolet catastrophe, and of course that's where the concept of H came from, Planck's constant. And H is just the smallest packet of energy, this quanta of energy that you can ever have. And just to refresh, you guys should be familiar with this, I presume, that value is approximately 6.626 times 10 to the negative 34 joule seconds. Okay, this is the fundamental unit of energy. That is to say that energy is quantized, so you can only have certain integer values of energy. You can have 1 times h, for example. You can have 2 packets of energy and 3, but you cannot have 1.5 h. Okay, you cannot have non-integers. That's just simply not allowed. So quantum mechanics is kind of interesting, because when in classical mechanics, if I have some sort of object, right, like a ball or some sort of particle in classical mechanics, and I apply a force to that particle, using Newton's law, the kinetics, which are all derived from Newton's second law, I can, and as long as I know the forces, so I know the force that I applied, I know the force, okay, of gravity, I know the forces of friction. I know all the forces. I plug them in, and I can plot a trajectory for that. So maybe the particle's here, and it has a certain trajectory, right? And I can arbitrarily know at any point of my choosing along that trajectory exactly where that ball is. one of the consequences of quantum mechanics due to this quantization in a certain sense is that you can't have a trajectory where you arbitrarily know exactly where this particle is and what it's doing. You can know, again, you have one, you have two, you have three, and you don't have anything in between. So the stuff in between is more or less irrelevant. And this, of course, fundamentally goes to what's known as the Heisenberg uncertainty principle, and I'm not really going to talk about that here. Um, but needless to say, the Schrodinger equation has to take in all of that interesting stuff into account. And here I have just one example. This is probably the simplest, the reduced way of looking at the Schrodinger equation. It's certainly my style, since I am not a adept at quantum mechanics, and it's certainly not something that I've studied, so I really don't have any business jumping into formal discussions on solving the Schrodinger equation and et cetera, aside from some basic concepts. And some of the concepts I want to talk about today, just because they're kind of interesting. And just to recap, the Schrodinger equation, basically in quantum mechanics, all your observables, things like energy and momentum and position, and those kinds of things, your observables are expressed as operators. So here I have this little guy here. This is known as the Hamiltonian operator. A little hat on top of the H says it's an operator. And basically what I put in here is I put the kinetic energy of the system that I'm looking at, the kinetic energy plus the potential energy. And that energy then operates upon psi, which is a wave function, which is a kind of in a sense, it's a physical description of the electron. Psi gives us information about the state of the electron after it has been operated on. And when we do this operation, what we do is we get back this E here. This E is actually constant. And because these operators in quantum mechanics, they're very special in the way that they're set up. And again, I'm not really going to talk about the formalism, but you can there are specific sets of solutions for this operation, and these can be formally talked about in if you take a linear algebra class and you talk about matrices, you can get what are called eigenfunctions, and then the solutions of those functions would be eigenvalues, and that's what this E is these are eigenvalues, and specifically the eigenvalues represent a very special kind of energy, and that is the binding energy of the atom. So it's basically the energy that, if you have the nucleus here, okay, a positively charged nucleus, and your electron somewhere there, it's the energy that binds that electron to the nucleus for a certain solution, a certain set of solutions of psi. And that's really handy because we can test the solutions using spectroscopy. We can give this electron energy and bump it up to a higher energy level. We know those energy levels are quantized, so the differences between the energy levels we should be able to see, because as the electron drops down to lower energy levels, it'll emit light, and the light has very quantized, quote unquote, very specific energies, so very specific wavelengths of light be given off. And of course, the binding energy is really helpful because we can look at things like what's the first ionization energy for a certain atom, How will these the valence electrons particularly, how are they energetically going to interact with other atoms, um, and so on and so forth. And then we get the wave function back. Now I should say that the form this form of the Schrodinger equation is time independent, so it doesn't really depend on time, and there are time dependent forms as well. But in just your run-of-the-mill problem where you have a nucleus of an atom, okay, with positive charge, and then you have an electron somewhere, orbiting in an orbit, quote unquote, around the proton, and you're not doing anything to the atom. You're not perturbing it. You don't have it exposed to a magnetic field. It's it's very cold. It's close to absolute zero. There isn't chemical bonding. You don't have anything else going on other than this system. This atom basically is a system sitting all by its lonesome. Then time really doesn't play any sort of role in how the evolution of this system. It's just sitting there. It's not doing anything. So we can look at an atom all by its lonesome, a hydrogen atom specifically all by its lonesome with this type of formulation. Okay, so that's a time independent Schrodinger equation, and all of that was just a whole bunch of filler. And I know some people kind of hate the filler that I do in my videos, but it's always nice to kind of provide a little bit of context in my videos. So what the heck. Okay, so going back to what I wanted to talk about, you get solutions. Solutions fall out. You solve the energies. You solve for the binding energy, and then you solve for the wave function. And your binding energy is your quantum number n, okay? And n is often known as the primary or principal quantum number. It really tells you what energy level, and the n can take on any integer, non-zero integer value. So 1 would be the ground state, 2 would be the first excited state, 3 the second, 4, okay, 5, 6, and so on. Okay, so that's the energy. And then you have L, little case L, and L, people often call this the orbital. Okay, the orbital. The orbital or the azimuthal quantum number. My computer is really slowed down for some reason. It's kind of lagging there. And we generally say the general rules for L is that L can go from 0 to n minus 1. Okay, so if I have n equals 1, then the only value of L I can have is 0. And again, L is quantized, 0, 1, 2, 3, 4, etc. Quantize integer values. And then I have my m sub L, or m, and most people call this the magnetic quantum number for reasons that will hopefully become a bit more obvious as we move along in this video. And typically people say, oh, the magnetic quantum number is the orientation of the orbital. And it is, but I'm going to actually be talking about this and L in a little more detail in this specific video. Okay, so that's the magnetic quantum number, and if you remember from general chemistry, the magnetic quantum number depends on L. And the magnetic quantum number can go from negative L, okay, negative L to positive L in discrete steps as well. So negative 1, 0, 1, 2, 3, etc. All right, and then your m sub s, which is your spin quantum number, and we know that that only takes on 2 states, plus 1/2 or minus 1/2, or some people say up, down, whatever, what have you. Red, green, blue, black, whatever. Two different states there. Okay, so that, excuse me, that is that. So what I want to do now is I kind of want to talk a little more about these quantum numbers in some detail here. So let me erase this. All right, so what I want to do now is I want to talk about L and really what L is. Okay, so here we have L. So when we go through the quantum mechanics, I want to give you guys just a quick qualitative thing here. Okay, so imagine that I have a nucleus. Maybe I'll do it down here. Okay, so here I have my nucleus, and here I have my electron. And we'll say, even though we know this is not true, but let's just say for now that the electron is orbiting the nucleus. There is some sort of motion going on that is roughly analogous to orbital motion in some sense. It's orbiting in quotes. Now, because I have a charged object that is accelerating, it's moving, that charged object is going to be, it's going to have some sort of angular momentum, all right? Angular momentum. Okay, right? It's obviously if it's moving in a circle, of course it's going to have some sort of angular momentum. It's going to have angular momentum, even if it's not literally orbiting. If there's some sort of orbit-like motion going on, it's going to have angular momentum. Okay, it's going to have angular momentum, and because it has angular momentum, and it's charged, the electron's charged, it's also going to have a magnetic. It's going to have a magnetic dipole, okay, a magnetic dipole moment associated with it as well, right? It's going to have a magnetic dipole moment associated with it in addition to angular momentum. Just like if it's kind of hard to draw here, but if you remember back from physics, the right-hand rule and how it applies to if you have a current, so let's say, I have like a current flowing in this direction here, and I'll wrap my right hand, okay, with my thumb. So my thumb will be facing in the direction of the current, and then I'll wrap my right hand around the wire like that, and how my fingers curl around that wire that current's going through, that's the dipole moment. That's how the magnetic field is oriented, that's being created by that current. Well, somewhat of an analogous situation is happening here. There is a magnetic dipole moment associated with an electron, its motion, if it has angular momentum. Okay, so hopefully everybody is okay with that, and you understand kind of what's going on there. Okay, so L, let's go back to L here. L, where does L come from? Well, L comes from the concept of total, okay? The total angular momentum of an electron in an atom is denoted by capital L. Okay, so the total angular momentum equals capital L, and capital L. Okay, capital L equals the square root. All right, equals the square root of little l multiplied by L plus 1. All right, L plus 1, and that's all multiplied by h bar. So h bar is just Planck's constant, h bar. Okay, h bar is just Planck's constant, h over 2 pi. It's what we call the reduced Planck's constant. So, all right, so this is actually where lowercase l comes from. Okay, it comes up in how we define the total angular momentum of an atom, or of an electron in an atom, excuse me. Okay, so that's really what L is, the quantum number L. L, little case l, is just a way, it is a way, okay, a way of looking at the angular momentum, a way of looking at angular momentum of an electron. Okay, it's not the total angular momentum, but it is a way of looking at the angular momentum, contextualizing it a little bit. Okay, now if I were to look at just a specific part of the angular momentum, okay, if I were to look specifically at the z, okay, I guess I could choose any axis or any component, but for this sake, for this today, what I'm talking about, we're just going to look at the z component. Okay, we're going to look at specifically at the z component of the angular momentum. Okay, and I'm going to call that L, capital L sub z. That's the z component of the total angular momentum, and that, okay, equals an integer value, m sub L times h bar. Okay, so here I have my my second and third quantum numbers are coming out of these concepts here. Okay, this is L, and this is m sub L. Okay, and m sub L, if you want to look at it, m sub L is the z component, which is a way, okay, it is a way of not looking, it is a way of looking at angular momentum, but it's a way of looking at the magnetic dipole, moment. Okay, it's sort of a way of looking at the magnetic dipole moment. More specifically, what we can say is it's that, as well as a way of looking at, so L is just a way of looking at angular momentum, right? It's L is kind of like the magnitude in a way. Okay, what's the it's not exactly, but it's kind of like, what's the magnitude? And then the m sub L, okay, the m sub L is kind of a way of looking at the direction. Okay, okay, it's a way of looking at the direction. How is the angular momentum oriented in the atom? What direction is it oriented in? Okay, so what I want to do now is I want to kind of just go through this, even if this isn't making a whole lot of sense. And what I want to do is I want to give you guys a specific n. I'm going to give you n equals 2, and then I'm going to give you L equals 1. Okay, so n is the second energy level, okay, and then L. So how many values of L can I have? Well, I can have 2, right? I can have 0 and 1. We're talking about 1, and if you remember looking at L, 0 another way of saying of identifying 0 is by calling it an s orbital, and 1 is a p orbital, and 2 is a d orbital, and 3 is an f orbital, f, g, etc., etc. Okay. All right. So how many values given n equals 2, l equals 1, and then m sub l, Okay, how many values of m sub l can I have? Well, remember talking about the rules. The rules tell us that we can go from negative l to positive l. So I could go, we'll start at positive l, so I could have 1, 0, and negative 1. Okay, so what does that mean? Well, what that means is that m sub l has 3 different orientations, so there are 3 different directions, quote unquote, of the z component of the angular momentum that I can have in the atom. I can have a 1 times h bar, 0 times h bar, and a negative 1 times h bar. So what I kind of want to do is I want to run through some basic math now, and we'll see if we can work through this and make some sense of this. So what I'm going to do is let's go ahead and find the magnitude of the angular momentum. Okay, so let's find the magnitude here. All right. So L equals capital L equals the square root, all right, of, and L is 1 in this case, so it's going to be 1, okay, times L again, so 1 plus 1, all of that multiplied by h bar, okay? So 1 plus 1 is 2, 1 times 2 is 2, all right, and so L, capital L, is going to equal the square root of 2 times h bar, okay? And what's the square root of 2? What is that about? What is that, approximately 1.4 h bar, thereabouts, 1.4? Yeah, close enough for government work. I'll go with that. Okay, so what I want you to do now is I kind of want, what I'm going to do is I'm going to draw, I have an x, y, and z axis here drawn, and this is going to kind of help us visualize what in the hell is exactly going on here to some extent. So what I'm going to do is I'm going to draw a sphere, okay, on the x, y, z. Imagine that this is a sphere here, okay. Imagine that this is a sphere, okay. And then what I'm going to do is I'm going to say that the radius, okay, so I'm going to start right here at my origin, and I'm going to say that the radius of that sphere, r, the radius of the sphere, r, is going to equal, excuse me, is going to equal the magnitude of the angular the total angular momentum, L. Okay, so r is going to equal L, which in this case is going to equal, let's see here, the square root of 2 times h. Okay, so h bar, I believe. Yeah. Okay, so let's just imagine that this line coming out here, this r here, okay, that line there, and I'll just draw an arrow to it. That line there is r. Okay, that's the radius, so that's the magnitude of the angular momentum, and that's going to equal the square root of 2 times h bar. Okay? Now, what I can do is, what is the z component? Okay, what is the z component of L? And let's just go ahead and choose, let's choose this one here, 1. So if m sub L equals 1, okay, if m sub L equals 1, what is the z L sub z? Okay, well, let's just go ahead and plug that into our formula since we have that. L sub z equals m sub L 1 times h bar. Okay, so it's h bar. Okay, it's basically just h bar. So now what I'm going to do is, because that this is z, what I'm going to do is I'm going to say that okay, so here I have the magnitude coming out, and then what I'm going to do, and let's just choose a different color here. I am going to make the z component. Okay, so what I can do is I can take a line here and I can drop this line straight down here. Okay, and if I drop this line straight down here, and this line is oriented in the z direction, and I make this come out at a point where when I drop this down, the length of that line there, okay, and that line is along the z-axis, okay, the length of that line, I am going to make h bar, okay, or 1h bar, okay, I'm going to make it this right here, okay. Okay, so I've plugged, basically what I'm doing is I'm trying to visualize the L. I'm trying to visualize the magnitude of the angular momentum and the orientation. Okay, so now what I'm going to do is, once I have this and once I have this proper length here, the magnitude, and this line here is the proper length, okay, this creates two different triangles here, and it's the angle that I'm most interested in is this angle right here, okay, that angle right there. If I can find that angle out, okay, that's going to tell me something really important about this. Now this angle is rather difficult to find, but if we go to the second triangle down here, okay, this second triangle down here, I know that this is a 90-degree angle, right? And if I know that, and I know the length of r and the z component here, okay, I can use basic trigonometry, right? You guys remember SOHCAHTOA, my basic, trigonometry, sine, okay, some old hippie caught another hippie tripping on acid, or SOHCAHTOA, sine equals opposite over hypotenuse, okay, sine of this angle right here, okay, and I could just call that whatever, theta or whatever. So sine of this angle here, okay, equals opposite over hypotenuse, right? So that's going to be a square root of 2 times h bar over h bar, and I'll spare you the math, but that angle here is 45 degrees, okay? Well, I know that the entire, from the z to the y, okay, this angle here is 90 degrees, so if I figured this bottom angle out, 45, then this angle here pretty much has to be 45 degrees. So what I've done is I have now solved for the not only the magnitude but the direction of the angular momentum, but because of the uncertainty principle, the interpretation of this is going to be very different. Okay, so what I'm going to do is I'm going to draw another. Maybe I can choose just a totally different color here, like maybe yellow. Okay. Okay, so I'm going to draw another line here at 45 degrees. All right, and then what I'm going to do is I'm going to draw this out like so. And I'm going to draw this out like so, and this will continue, okay, to go out. Okay, so now imagine that this is kind of like a cone, spreading out in 3 dimensions. So I'm going to do my best to make this 3-dimensional like that. Okay, so you can see that I have the z-axis, and I'm going to just draw the z-axis coming up Okay, so the z-axis is coming out the middle of this cone, and what this is telling me is that the z component of the angular momentum is 45 degrees off of the z-axis. Okay, it's 45 degrees off the z-axis, but I can't know exactly where the angular momentum is due to the uncertainty principle. I just know that it's 45 degrees off of the z-axis, and so the angular momentum, the direction of the angular momentum, could be anywhere kind of along this sphere, or this conical three-dimensional shape that's oriented at 45 degrees off. So that would be 1. Okay, that would be the m sub l equals 1. And let's just choose a yellow again here. All right, maybe. There we go. All right, so let's say that I made m sub l negative 1. Well, that's just going to be minus this, so it's going to be a 45 degrees shooting out in this direction, okay? And it'll be that's pretty terrible. Going to be kind of the same situation, okay, if you can imagine a cone. And then 0, okay, m sub l equals 0. Well, that's just going to be kind of like that in a certain sense, right there at the xy, on the plane, right along the plane of the xy axis. So you can see that there's a much deeper interpretation of the quantum numbers, and this becomes relevant because this is the orientation of the magnetic dipole moment. And if I have a certain electron that has a quantum number, m sub l negative 1 or 2 or 3 or whatever, that electron is going to be influenced differently by magnetic fields than other electrons. And when we look at the fine structure of the spectroscopy of atoms, we can get some line splitting, particularly when we expose these atoms to magnetic fields. I believe it's called the Zeeman effect. And having a little more in-depth appreciation of what's going on here can help us understand that. And it also can help us understand what is going on with the p orbitals, because that's all I've been talking about here. These are actually p orbitals, and I'm talking about how the angular momentum and the magnetic dipole moment of the p orbitals is oriented. And in the next video, I'm going to go ahead and pull up Atom in a Box, and I'm going to show you I'll show you visually how we can do we can take linear combinations of the p orbitals and make them into the kind of orbitals that we need. We can kind of make a different type of orbital that is more relevant for chemistry. I think I'm going to cut it off here. I've probably gone way over, probably much longer than I should have gone. But I hope to get this video up, and I hope you guys do enjoy this. As always, thanks for hanging there.